Alright, this lesson is going to be all about double replacement reactions, and just as a reminder, this is where you have two couples and they both switch partners, so you end up with two new compounds on the other side. So the rule is, in order for a double replacement reaction to occur, one product has to be either a gas, a liquid, and the only liquid you'll see is water, and then you've got this new vocab right here, precipitate. So it looks like the word to precipitate, which is a verb, and it means to rain or snow. It's spelled the same, but you say it a little bit different in chemistry, and this one is a noun. So this means when you mix two liquids together and they form a solid, it's called a precipitate, and it's going to look cloudy. So when you see the word precipitate, you need to think of solid and cloudy. That will help you remember what that word means. If all the products are aqueous, which is another vocab word, aqueous means dissolved in water, it will not occur, and I'm going to show you why in just a minute. And for this, you're going to use the solubility rules, and in the solubility rules, there are two categories. Soluble, sol means to dissolve, able means able, so soluble literally means able to dissolve, so that one dissolves in water. In, it means not, so insoluble means not able to dissolve, so that means it's going to be a solid precipitate. Here's the problem though. You see how soluble looks like solid, or it sounds like solid? So a lot of people confuse those two. So try to just remember that soluble does not mean that it's a solid. Let me show you what's going on down here, and then I'll show you how to do the reactions. So first of all, if you have this reaction down here, we've got AB, and remember AQ means that it's dissolved in water, which really means that these particles are separated as ions and they're floating around. So anytime you have an AQ ionic solution, it really means that it's a soup of charged particles. Notice that CD is as well. Now we're going to switch the partners, so A is bonded to D, C is bonded to B, and we're going to put them all in the same container. If AD is AQ, that means A positive and D minus are floating around, and CB is also AQ, that means C positive is floating around and B positive is floating around. Notice that nothing has changed. We started with two soups of floating ions. We ended with a soup of floating ions. They're just floating ions. Nothing has rearranged and nothing has formed something different. And so that is when we say it's a DNR, if both of the products are AQ. Don't worry about the reactants. We don't care about them. They're going to be AQ to start with. What we're looking at is if the products are still AQ. Let's say that one of these, let's say that the AD is actually a solid, if it's insoluble. What that means is that in this soup, A and D are going to combine. So we still have C positive and B minus floating around, but A and D are going to combine and form like a paste at the bottom down here. That would be the AD solid. And that's different. So notice that we now have a solution that looks different from what we started. We don't just have floating ions anymore, so that's when we say it reacts. It doesn't matter if both of the products are solid, or if you get a solid and a liquid, and again, the only liquid you'll see is water. What you're looking at is if you get two AQs, that's when it's going to be a DNR. So let me work through a couple of these with you. First of all, you're going to need your solubility rules, and they look like this, where it's a list of things that are soluble, list of things that are insoluble. Alright, just like single replacement, this is going to be a series of steps. You just have to go through the steps for each reaction, and you'll end up with the right answer if you go through the right steps. The first thing you want to do is, just like single replacement, you want to put charges or oxidation numbers on all of your things. And actually, let's go ahead and put charges. Yeah, we'll go ahead and do this one. So put charges on everything, and then you're going to rearrange your partners. So we're going to put barium with phosphate, and we're going to put hydrogen with hydroxide. Now, one thing to notice, I didn't bring the 2 or the 3 across the arrow. Just like single replacement, do not bring those numbers across the arrow unless it's part of a polyatomic ion. So the 4 did come with me, but the others did not. Barium is +2, phosphate is -3, so we need to cross those charges down. And then H is +1, OH is -1, so those cancel out. Now normally we're going to use the solubility rules for double replacement, but here's the thing. If you ever end up with HOH as a product, that's really water, because you know how water is H2O, so if you separate the hydrogens you get HOH. That's a liquid, and a liquid is not AQ. So you automatically know that this reaction is going to react anytime you get one that has water. So now we just need to balance it. Looks like we need a 3 here for the barium, we need a 2 here for the phosphate. And then be careful, you can balance the H separate from the OH. I think it's easier to see that if you write water as HOH. So 2 times 3 is 6 hydrogens here, and we have 3 times 2 is 6 OHs, and so we need a 6 for the water so that we have 6 hydrogens and 6 OHs. And a trick for water is if you save the H and OH for last, you should have matching numbers of H and OH on the left. So you notice how they're both 6, and that's the number that water gets. And we'll do another one with water in a few minutes. One of the ones at the bottom is like that. All right, let's look at the next one. First thing you're going to do is put charges on all 4 things. So remember, single replacement had 3 things, double replacement has 4. So you can look all of these up. K is +1, sulfate is on your list of polyatomic ions, and these last 2 are on the periodic table. Then you're going to switch the partners, but keep it plus minus, plus minus. So we're going to put calcium with sulfate. You can bring that 4 because it's part of the SO4, and we're going to put K with Cl. Notice I didn't bring those 2. The only time, the 2 2s. You don't bring numbers across the arrow unless they're part of a polyatomic ion. And we do need to cross charges, but I think everything cancels out here. So calcium is +2, sulfate is -2, K is +1, Cl is -1, so they all cancel out. So the next thing we want to do is to see if this reaction is going to occur. And what you're going to do, again, only focus on the products, what I wrote in red. Don't worry about the reactants. Then you're going to look at the second half of them. So they belong to the family that is the second part of their name, just like your family name is your second name if you only have 2, if you know your middle name. It's like your family is the end of your name, and it's the same with chemicals. So that first compound we say belongs to the family of sulfates because it has a SO4. So look at the second thing there. So now we're going to go over to the solubility rules, and you need to find where it says all sulfates, and it says it right here. All sulfates are soluble, and before we do this, let's go ahead and just make a little note. Soluble, if you can write on your reference tables, put a little AQ here and put a little S there to remind yourself that soluble means it's AQ and insoluble means it's a solid. So sulfates fall under the category of AQ, which means that most sulfates are aqueous. Most of them will dissolve in water. However, there's a few exceptions. So anytime you look at these lists, you not only want to see what category it fits into, but you want to read the list of exceptions to see if it's bonded to that exception. And notice what that first exception is calcium, which is what we have. So if it fits the exception, it bumps it into the other list. So because this is an exception, it's actually going to be solid, even though most sulfates are AQ. So we automatically know that this reaction will happen because we got one product that was not AQ. Again, the only time it's a DNR is when you get 2 AQs. Let's go ahead and check the other one just for practice though. Again, for KCl, you're going to look at the second half of it. So this belongs to the family of chlorides. So let's find that over here on our list. Chlorides are this one right here. All chlorides are soluble, so most of them are AQ, unless they're bonded to silver, lead, or mercury. So there's only 3 exceptions here, and potassium is not one of them. So it's going to remain in that list. It's not going to get bumped into the other list. And that means this one is AQ. So again, we know this reaction will happen because we got a solid. If you get H2O or if you get a solid, the reaction will happen. So the last thing is we just need to balance it, and I think we just need a 2 right here to fix the K and the Cl. All right, let's do one more together, and then let's try those last 2 by yourself. For this next one, again, you want to go ahead and put charges on all of your things. So you should end up with 4 charges. This is different from yesterday. Yesterday we only did 3. And that's where we did the activity series. This is where you're doing 4 and you're doing the solubility rules. Now the problem here is iron. Iron's a transition metal, so you're going to have to set up that little X equation to figure out what iron is. You can probably kind of figure it out just looking at it. If you know that the compound needs to add up to 0, and you can see that bromine is going to be -2 because we have 2 of them and they're -1, so that means that iron is going to have to cancel that out. So now I can tell that iron is going to be +2. You can set up the X equation if that's easier for you though. All right, we're going to switch the partners, but keep it plus minus plus minus. So make sure the positives are always first, and make sure that you switch the partners. So aluminum is going to go with bromine, and iron is going to go with chlorine. Notice I did not bring those numbers across the arrow. The only time you do that is if it's part of a polyatomic ion. Iron we said was +2, so we need to bring that down to chlorine, and aluminum was +3, so we need to bring that down to bromine. So don't forget to cross those charges. All right, let's see if this is going to react. The first one is a chloride, which actually I already had circled. All chlorides are AQ. Let's check these exceptions though. It's bonded to iron in the compound, and I don't see iron as an exception. Silver, lead, and mercury are the only exceptions, so it's going to remain in the AQ category. And we're ready to check bromides, which is exactly the same list. So bromides are also AQ unless they're bonded to silver, lead, or mercury. Aluminum is not on that list. And now look what happened. We got 2 AQs. This is the time that it's a DNR. So if you're taking a quiz or a test, you need to show somewhere in your paper that this reaction does not happen. And you actually don't even have to balance it because it's not even a reaction in real life. All right, pause this video. I'm going to write out the answers to the next 2, and then you can check your answers. All right, check your answers for these last 2. They both should react. So in the second to last one, you should get HOH, which is water, and that's a liquid. Be careful balancing this one. So like I said before, it's easier if you save H and OH for last. So go ahead and do the K and the SO4 first. That's how I got the green 2 all the way on the left. And then if you balance that correctly, you always will have matching numbers of H on one compound and OH on the other. So notice we have 2 and 2, 2 OHs and 2 Hs. That's the number that water gets. I know those can be a little bit tough to balance. All right, this last one, if you switch the partners, you get NH4Cl and CaCO3. One little side note, it's okay to switch those around the plus sign. So if you put NH4Cl as the last compound and CaCO3 as the first compound, that's perfectly fine. The main thing is within the compound, it would be wrong if you put Cl and H4. You have to put the positive one first. The charges all cancel out on those, and if you do it correctly, you should get AQ for the first one, because if you look up here, chlorides are AQ, ammonium is NH4, and it's not one of those exceptions. And then carbonates are down here in the insoluble list, and there's a couple of things. One is that notice that it says group 1. That means the alkali metals. Group 1 is the first column on the periodic table. So calcium is not an alkali metal, it's an alkaline earth metal. It's the second column. So it doesn't fit the exception, which means it stays in that category. And again, insoluble means that it is solid. So that one will react because we got a solid, and then to balance it, you just need an NH4, a 2 in front of the NH4Cl to fix that balancing. And one more thing I just wanted to make a note of that I see a lot of people mess up on. If you have something you can write on for your reference tables, I want you to circle this word right here and just be really careful with that word. The word is and a lot of people read that word as except. So for example, if you had NaNO3, they would look at nitrates and they see that nitrates are soluble, then they keep reading and they read and group 1. Sodium is group 1 and they think that's an exception and bump it into the other category. So for this first rule right here, there are no exceptions. For that first rule, if you have any nitrate, any acetate, any ammonium, or anything with group 1, meaning any alkali metal, it's automatically going to be AQ and it's not going to be a solid. All right, these take a little bit of practice. You kind of have to go through the steps a few times before you get it. So take a look at your progress check and try those by yourself, and then check your answers and see how you did. Good luck.